Hi again, my name is Phil Mateus, and welcome to the part 2 of my talk, Commensurating HTML Extensions and Bioautomaticity. Just a short recap from part 1. What did we discuss? Well, we discussed the following two results, which we aim to prove here. The first result is that there exist Cat0 groups that cannot be subgroups of bioautomatic groups. And the second, based on joint work with Sam Hughes, is that there exist hierarchically graphable groups, HAGs, which are not bioautomatic. We also introduced our groups, and we show that our groups act geometrically on a probability cross V, where T is a locally finite tree and V is either either a Euclidean space or the hyperbolic plane. The projection of gamma onto the isometry, the projection of gamma to the isometry group of V has non-discrete image. So this is a fact we haven't used yet, but we will use in this part of the talk. And we also know that the action on T has a vertex stabilizer that is commensurated and alpha is a convex for any bioautomatic structure on gamma. So this vertex stabilizer will be denoted by G in here. And we know that if gamma is bioautomatic, then using alpha as a convexity, we can show that G has a nice bioautomatic structure. And we use it to study this function defined by this formula, and that's just a function that we call the M translation length. And the fact that G is commensurated tells us that this function is in some sense gamma invariant. Okay, so this is what we want to study, and this is what we want to prove in this part. Now we start by discussing what sort of things we can take as a boundary of a group G. So suppose our group G has a bioautomatic structure. We would like to introduce some sort of boundary that allows us to study this M translation net. The good news is that there exists a boundary introduced by Neumann and Shapiro, and it is a boundary defined as collections of fellow traveling words in our language M under some suitable equivalence. And this boundary works for any bioautomatic group. And let's look now in our specific cases. So when G is free abelian, then this boundary will actually be finite. So maybe not what we would expect initially, but it's still useful. And it has been used in the first proof of Ian Lehrer and Lars Manasian to show that these groups gamma that we consider are actually not bioautomatic. So they are Cat0 groups which are not bioautomatic. Now we want to show something stronger. So we want to show that these groups cannot even be embedded in a bioautomatic group. And for that, we consider something called the rehabilitated boundary, again introduced by Neumann and Shapiro in the same paper. And this is just a triangulation of the M-1 sphere for the free abelian group. So it's what we would expect to have for a boundary of ZDM. So that's the situation in the Euclidean case. Now in the hyperbolic case, the situation is different. So the boundary that we have for any hyperbolic group, for any bioautomatic structure in a hyperbolic group, the boundary of this bioautomatic structure turns out to be just the Gromov boundary. So in our surface group case, this will be just a circle. But this is where the good news ends, and unfortunately, it is not clear how this M translation length could induce a continuous function on this boundary. And even if we could induce some function on this boundary, well, we know that this translation length is invariant under conjugacy by elements of G. But this quotient, boundary of M divided by G, this does not seem nice. So this quotient will not be Hausdorff, will not be metrizable, will not have any nice quotient. So whereas if we could use M translation length to induce a continuous function on this boundary, then to also induce continuous function on this quotient. So yeah, we run into some sort of trouble here. So what we do, well, we do something completely different. So we ignore this biautomatic boundary and consider instead a space of oriented geodesic currents on our surface. So I will introduce this later, but just to list some properties that will be important for us. Well, this still looks like a boundary, so it has something that some properties that you would expect from a boundary. On the other hand, this M translation length does extend or does induce a continuous function on this space of currents. So this is what we want to use, and this is what we will use. But first, let's start with the Euclidean case, and let's study the geometry of this M translation length function in abelian groups. So let's suppose we have an abelian group, which has a biautomatic structure. So let's suppose for simplicity that G is just ZVM, so it's a free abelian group, and it has some biautomatic structure, and we consider this translation length. So instead of a function from Z to the M to R, we can think of a function from R to the M to R, just by tensoring with R. And this turns out to be nice. So in particular, it's what I call a polyhedral function. To define it, let's start with the definition of a cone. So a cone in Rm is just the set of sum of non-negative linear combinations of some base vectors or some fixed bases of Rm. And if we have a finite collection of these cones form a cone subdivision of Rm if Rm is the union of all these cones and the intersection of any two different cones in our collection as empty interior. So we can think of Rm, we can think of a cone subdivision as just a triangulation of the M-1 sphere when we project Rm to just the M-1 sphere. And in our particular case, this triangulation of the M-1 sphere will be precisely the rehabilitated boundary that we have talked about in the previous slide. So that's good. So this is how everything is related. And we say a function is polyhedral. So a polyhedral is just a property that we already said this translation length satisfies. A function is polyhedral if there is a cone subdivision such that the restriction of a function to any of the cones is linear. So that's all it is. So to understand this better, let's look at an example. And for an example, let's look at this particular biautomatic structure on Z squared. So this is perhaps looks a bit complicated, but it is actually not. And the reason is because all biautomatic structures on abelian groups look more or less like this. So they're a union of things where each of these things in the union correspond to a cone. So here the colors of the expressions correspond to the colors of these wedges, which of our pi, which is r squared in this case. And the cones are defined by basically these expressions in the parentheses for which we put a star. So we can think about these expressions as some vectors. So for instance, here epsilon xy squared is just vector 1, 2. Epsilon y is just a vector 0, 1. So we can think about a cone corresponding to these vectors 1, 2 and 0, 1. And it will be exactly this purple section in here. And similarly, for all the other expressions, we have some cones corresponding to it. So in here, we have some cone subdivision that we can just read off from this language M. And we also know that this M translation length is polyhedral, and well, basically, I hope this makes it clear why it's polyhedral. It's just because in each of these cones we have some expression that sort of looks like linear. And now, why do we call this function polyhedral? Well, this is because if we look at the preimage of any positive real number under this function, which is polyhedral, we get some polyhedron. And if we change the number t that we take here, we get a rescale copy. So basically, we get just rescale copies of some given some fixed polyhedron. So this is more or less how bioautomatic structures, or how this translation lens on bioautomatic structures on abelian groups look like. Okay. So now let's put everything together into a proof. So suppose we have a commensurate negation extension of a free abelian group, and suppose we have the stable letter acting by an infinite order isometry. So we could take an infinite order rotation, which is nice enough to commensurate a finite index subgroup of ZDM. So it's nice enough basically to define a commensurate engagement extension. Now, the fact that the stable letter acts by an infinite order isometry tells us that if we take gamma and just look at the action of the stable letter, so we project gamma to OM, this group will be infinite. And this is basically where we use the non-discreteness part of our projection. Now, suppose we have a bioautomatic structure for some group containing gamma. So some gamma hat containing gamma. Now we do the following trick. So given this subgroup G, we can actually find a finite index torsion-free subgroup of the center of the centralized of G containing G. So this is just an algebraic fact. But the fact that we can take a center of the centralized of G, well, we know how centralizers behave in bioautomatic groups. And we know that they are quasi-convex. So actually this group will be L hat quasi-convex, and therefore G hat itself will be L hat quasi-convex, as it has finite index in an L quasi-convex subgroup. So we have an L hat quasi-convex subgroup, which is free abelian and contains our subgroup G. And now the point is that since this function associated to a bioautomatic structure on G hat is polyhedral, we can restrict this function to a subspace, which corresponds to the subgroup G, and that function will still be polyhedral. So basically, if we take a polyhedron and we intersect it with some subspace of Rm, what we get again is a polyhedron. That's the point of all this construction. And the fact that G is commensurated in gamma now allows us to induce a gamma action on Rm, which is a G tensor R, and our function f is invariant under this action. So now basically we are not working in this big group gamma hat anymore. Now we have some structure on our smaller group gamma. And now we take any non-negative, let's say positive real number, and we look at this polyhedron F inverse of T. This polyhedron has symmetry group containing the projection of gamma to OM, but this projection gamma to ON by our construction is infinite. And that is impossible because we can't have a polyhedron with an infinite symmetry group. Okay, so this is how we show that we cannot have any bioautomatic group gamma hat that we introduced in step 3 containing gamma. Okay, so this was the proof in the Euclidean case. Now let's look into the hyperbolic case. In the hyperbolic case, let me quickly introduce the space of currents, or at least the facts that we use about occurrence in our proofs. So suppose now G is a surface group and we fix a Riemannian metric of constant negative curvature on our surface so that G acts on the universal color of our surface, which can be identified with a hyperbolic plane. Now, given a primitive element of G, which means it's not a proper power, the G conjugate class of this element defines a geodesic, which is just a map from a circle to our surface signal. And then now we look at all the lifts of our geodesic to the hyperbolic plane. So this defines some subset of this I plus of sigma tilde. This I plus of sigma tilde is just the set of all oriented geodesic lines in the hyperbolic plane. So we can check that this I plus of sigma tilde will be homeomorphic to an annulus. And if we look at all these lifts of alpha G to the hyperbolic plane, this defines a subset which is discrete and G invariant. So this is easy to check. And now we define a Borel measure on the set of oriented geodesic lines in the hyperbolic plane just by looking at the counting measure by intersecting everything with our set of our discrete G invariant subset of lifts of alpha G. So this is a G invariant measure. It is clear. What's less clear is that it's Rodon measure, and what's less clear maybe it's what is Rodon actually. But it basically means it's a nice measure, and we can check everything working. Now this defines this measures mu sub G for primitive element G. We can just extend this to all element G by setting the measure corresponding to G to the n just to be n times the measure corresponding to G, where n is a non-negative integer. Okay, and now we look at the measures basically like this, so satisfying the same nice properties. In particular, we look at the space of all G invariant Rodon measures on the set of oriented geodesic lines in the hyperbolic plane. We can equip this with some topology, so that makes this space into a topological space, and that's the space of oriented geodesic currents that we consider. And this satisfies some nice properties. So one of those properties is that positive multiples of our measures corresponding to group elements are actually dense in the whole space of currents. And another property is that if we projectivize this space of currents, this will be compact. So again, there are some nice topological properties of this space. And now let's study the properties of this M translation and function for surface groups. So for now, suppose that we have a bioautomatic structure on an arbitrary group G. And here we use the trick we used before. So given an element of infinite order, well, we already know how to embed an abelian subgroup, which in this case is just cyclic subgroup generated by G, into an L-quasi-convex abelian subgroup. In this case, M-quasi-convex abelian subgroup. So we just take the center of the centralizer, and we can pass to a finite index torsion-free subgroup containing our element. So this gives us an M-quasi-convex free abelian subgroup. So we will have an associated bioautomatic structure for this subgroup. The point is that we already studied the translation lengths associated to this new bioautomatic structure. So that was the point of our study in the Euclidean case. In particular, we know that there is a cone subdivision of Rm such that this translation length of any element H will be, when we look at the proof, how the proof goes, we can say that this will be just the inner product of H with some yi, where yi will actually be a vector with rational coordinates. Now, in particular, if we substitute the element G in here, G is an element in H, which we identify to Z with Z to the M. So it will be an inner product of an element of Z to the M with an element of Q to the M. So it will be a rational number. So it follows that for any element of G, this translation length will be rational number. But now this translation length coincides with the translation length with respect to the original bioautomatic structure we had. So from this, we can deduce that translation length of any element of G will be rational. Okay. So this is what we'll use later. And now suppose that our group is a service group as before, and we want to use this space of currents to study its translation length. Now there is a slight problem, is that this length of words in M representing G, this is not something that is invariant under conjugacy in our group. Well, the solution for that is to make it invariant under conjugacy. So we take just the minimum of these lengths, and when we look at the conjugacy class, and we look at the corresponding stable version. And it's clear from the definitions that this new translation length tau m prime will be at most the old length tau m that we introduced before, but actually for hyperbolic groups, we can show that the reversing inequality also holds. So these two will be equal things. Okay, so now in the remaining time, I would like to quickly go through the proof, but also see Sam's talk in the session on Teichmüller spaces and geodesic currents, where he will talk a lot more about all these ideas behind geodesic currents. Okay, so we can construct our group using quaternion algebras. So here, perhaps, I will not go into much detail, but the point is that we can construct this H&N extension of surface group. And we suppose that our group gamma is bioautomatic, and we set y comma m to be bioautomatic structure on the vertex stabilizer G. Now, since the image of gamma in the isometry group of hyperbolic plane is non-discrete, we can actually show that it is dense. And we can now use this new function that we just introduced, which is invariant under conjugacy, to define a function on the space of currents. So that's why we want to have something invariant under conjugacy to define a function on the space of currents coming from the elements of G. So this is basically just translating from the language of curves to the language of currents. And we can we can check that this function that we just defined satisfies some technical condition, allowing us to extend to the positively homogeneous function, in which it's continuous in particular. So this is a very nice thing with the machinery that we have. We have some continuous function defined on the space of currents. And the fact that G is commensurated allows us to introduce some, given an element of the projection of our group, we can have another map satisfying this property. And well, now we use the fact that this projection is dense. We can use it to show that this function f hat that we just defined will actually be very restricted. So it can be just k times some fixed current that we have. And this allows us to say that the translation length of an element is precisely k times the length of the geodesic representing that element. But now the ratio of these two lengths can be an irrational number. We can just check it in our group, and this contradicts the fact that all the translation lengths are rational numbers. So this is how the proof works. Okay, so this was the talk, and thank you for listening.